In 1928, a young British physicist named Paul Dirac sat down to solve what seemed like a straightforward problem. He wanted to write an equation that combined quantum mechanics with special relativity. Quantum mechanics had been spectacularly successful at describing atoms and electrons, but it was non-relativistic. It didn't account for particles moving at speeds approaching light, and special relativity worked beautifully for fast-moving objects. But it wasn't quantum. Dirac wanted both. He wanted an equation that was quantum and relativistic simultaneously. What he discovered would win him the Nobel Prize. It predicted the existence of antimatter positrons, antirotons, particles identical to their matter counterparts, but with opposite charge. When Carl Anderson detected positrons in cosmic rays 4 years later, DRA was vindicated. The equation worked. It was one of the greatest triumphs in theoretical physics. But there was a problem, a huge problem, and we ignored it. But the Dirac equation had solutions we didn't like, negative energy solutions. States where an electron could have less than zero energy falling forever into deeper and deeper negative values, radiating infinite energy in the process. This was physically absurd. Electrons don't do this. The universe would be unstable. So DRA proposed something radical, the Dirac sea. Imagine he said that the vacuum-empty space is not actually empty. It's an infinite ocean of negative energy electrons filling all of space, occupying every possible negative energy state. The reason we don't see them is because they're all occupied. Paul's exclusion principle says 2 electrons can't be in the same state. So if all the negative energy states are full, regular positive energy electrons can't fall into them. And occasionally, if you pump enough energy into the vacuum, you can promote one of these negative energy electrons into a positive energy state. What's left behind is a hole, an absence of negative charge, which behaves like a particle with positive charge, a positron. This was the Dirac sea, and it explained antimatter beautifully. But physicists hated it. An infinite sea of unobservable particles filling all of space, infinite negative energy density. It was ugly. It was baroque. It violated the simplicity that physics demands. So when quantum field theory came along in the 1940s and 1950s, developed by Feynman, Schwinger, Tominagas, and others, they found a different interpretation. They said, forget the sea, negative energy solutions moving forward in time are mathematically equivalent to positive energy antiparticles moving backward in time. It's just a reinterpretation of the mathematics. We don't need an infinite ocean of particles. We just need a clever change of perspective. And it worked. Quantum electrodynamics was born. It predicted the magnetic moment of the electron to 10 decimal places. It explained the Lamb shift. It became the most accurate theory in the history of science. But there was a cost we didn't realize we were paying. We threw away the direct sea. We declared it unphysical. We said the vacuum is truly empty and negative energy states don't exist. They're just mathematical artifacts we can reinterpret away. And in doing so, we lost quantum gravity for 50 years. Let me explain what we missed. The direct sea was trying to tell us something profound. The vacuum is not nothing. The vacuum has structure. It has energy. It has dynamics. And we know this now. We know the vacuum is filled with quantum fluctuations, virtual particles popping in and out of existence, zero-point energy oscillating at every point in space. The Casimir effect, where 2 metal plates in vacuum attract each other because the vacuum energy between them is less than the vacuum energy outside them. All of this is real, measured, confirmed. But we still treat it as a nuisance. When we calculate vacuum energy in quantum field theory, we get infinity, literally infinite energy density at every point in space. So we renormalize. We subtract away the infinity by hand, saying we only care about energy differences, not absolute values. This is mathematically consistent, but it's philosophically bankrupt. We're papering over the problem instead of solving it. We're saying the vacuum has infinite energy, but we'll just ignore it. And this works for particle physics, for predicting scattering amplitudes and decay rates. But it fails catastrophically when we try to connect to gravity, because gravity cares about absolute energy. General relativity says energy curves spacetime. And if the vacuum has infinite energy density, spacetime should be infinitely curved. The universe shouldn't exist, but it does. And the cosmological constant, the actual vacuum energy we measure from cosmology, is not infinite. It's tiny, 10 circumlex, 120 times smaller than quantum field theory predicts. This is the worst prediction in the history of physics, off by 120 orders of magnitude. And the reason we can't solve it is because we threw away Dirac's insight in 1928. The DRAS was telling us that the vacuum is a physical thing, not just mathematical background, not just a definition of zero energy, but a real structured dynamical entity that must be treated as part of the theory. If we'd taken it seriously, if Feynman and Schwinger and the quantum field theory pioneers had asked, what is the Dirac sea really telling us about the nature of spacetime? We would have discovered something astonishing. We would have discovered that spacetime itself is emergent from quantum information. Let me show you what I mean. In my work on twistor theory, I've tried to describe spacetime not as a fundamental thing, but as a derived thing, something that emerges from deeper geometric structures. Points in spacetime are not primitive. Light rays, spinors, complex projective spaces. These are the fundamental objects. Spacetime is what you get when you combine them in the right way. And if spacetime is emergent, then what is it emerging from? Quantum information. The Dirac sea reinterpreted correctly is the information substrate that underlies reality. Think about it. The Dirac sea says every point in space contains an infinite number of occupied quantum states. That's an infinite amount of information. And when you create a particle, antiparticle pair, you're not creating something from nothing. You're promoting information from the vacuum into an observable state. The vacuum is not empty. It's a library, an infinite database of quantum information, and particles are just temporary excitations, bits of information that have been read out, made visible, given energy. This is what the holographic principle discovered decades later. The idea that all the information in a volume of space can be encoded on its boundary surface, that three-dimensional reality might be a projection from two-dimensional information. But Dirac saw it first in 1928, and we ignored him. If we had pursued this line of thinking, if we'd asked, what does it mean for the vacuum to be an infinite sea of information? We would have been led inevitably to the conclusion that spacetime is not fundamental, and that would have changed everything. Quantum mechanics wouldn't just be a theory on spacetime. It would be the theory that generates spacetime. Gravity wouldn't be separate from quantum mechanics. It would emerge from the way quantum information organizes itself in the vacuum. We would have had quantum gravity by 1980, maybe earlier. Instead, we spent 70 years trying to quantize general relativity, trying to force spacetime to be made of tiny quantum chunks, trying to write Feynman diagrams for gravitons, trying to build a theory of quantum fields on a fixed space-time background, and it doesn't work. String theory requires 10 dimensions and has no experimental predictions. Loop quantum gravity makes spacetime discrete, but can't recover smooth Einstein gravity in the appropriate limit. Every approach that treats spacetime as fundamental gets stuck because spacetime isn't fundamental. Dirac told us this in 1928, and we called it unphysical. Now let me tell you the real tragedy. When Feynman developed his path integral formulation of quantum mechanics, he showed that you could calculate probabilities by summing over all possible histories, all possible paths a particle could take through space and time. This was revolutionary. It gave us a new way to think about quantum mechanics. But Feynman was deeply influenced by the reinterpretation of Dirac's equation. He embraced the idea that you don't need the C, you just need the mathematics. And this led him to treat spacetime as a fixed background, a stage where quantum processes happen. What if he'd gone the other way? What if he'd taken the direct C seriously and asked, what are all these negative energy states? What is this ocean of information? He would have been led to sum not just over particle paths, but over space-time geometries. He would have invented the path integral for gravity. He would have discovered that space-time itself is quantum, not because it's made of discrete chunks, but because it emerges from quantum information. Instead, that insight had to wait for Stephen Hawking in the 1970s, and even then, we couldn't make it work because we didn't understand what the vacuum really is. The Dirac C was the key, and we threw it away because it seemed too strange, too ugly, too laden with infinities. But infinities aren't a bug. They're a feature. They're the universe telling us you're asking the wrong question. When we get infinite vacuum energy, we shouldn't renormalize it away. We should ask, why does the vacuum have structure? What is that structure? How does it give rise to space-time? And the answer, I believe, is geometric. The vacuum is not a sea of particles. It's a field of geometric relationships, spinors, twistors, complex structures that encode information about how space-time could possibly be arranged. And when you excite this field, when you create a particle, you're not adding energy to empty space. You're making one particular geometric relationship manifest, observable, classical. Particles are not things in space-time. They're patterns in the information that generates space-time. This is what the Dirac equation was trying to tell us all along. And if we'd listened, if we'd taken seriously the idea that the vacuum is structured, that negative energy states are real, that the sea of quantum information is the substrate of reality, we would have understood by 1950 that spacetime is emergent. We would have seen that quantum mechanics and general relativity are not separate theories that need to be unified. They're two descriptions of the same thing, the way information organizes itself into geometry. Quantum mechanics tells you how information evolves. General relativity tells you what geometry that information creates. They were never in conflict. We just couldn't see it because we were asking the wrong question. We were trying to quantize spacetime instead of recognizing that spacetime is already the classical limit of quantum information, and this mistake cost us everything. 50 years of brilliant physicists banging their heads against the problem of quantum gravity. 50 years of increasingly elaborate mathematical structures, strings, brains, extra dimensions, multiverse, anthropics, all trying to avoid the simple truth Dirac saw in 1928. The vacuum is not empty, it's full of information, and that information is what space-time is made of. Now we're finally catching up the holographic principle. The EPR, equal sign, EPR conjecture, linking wormholes and entanglement. The idea that spacetime emerges from quantum entanglement. All of this is converging on the same conclusion. But we lost a century, an entire century of physics chasing the wrong formulation because we didn't trust what the mathematics was telling us. Dirac's equation had two solutions. We kept the one we liked, antimatter, beautiful, measurable, Nobel Prize worthy, and we discarded the one we didn't like. The infinite C, ugly, unphysical, embarrassing. But the C was the answer. It was always the answer. And if a young physicist in 1930 had been brave enough or crazy enough to take it seriously, to ask, what does an infinite information substrate really mean for the nature of space-time, we would be living in a different world. We would have quantum gravity. We would understand what happened at the Big Bang. We would know whether black holes destroy information or preserve it. We would have a complete theory of everything, not string theory, speculation, or loop quantum gravity discreteness, but a genuine geometric understanding of how information becomes space-time, becomes matter, becomes consciousness. Instead, we're still searching, still trying to reconcile quantum mechanics with gravity, still treating space-time as fundamental, when the equation we derived in 1928 was screaming at us, it's not fundamental, it's emergent, it's information, it's geometry. We solved the wrong equation. We took Dirac's masterpiece and said, this half is useful, this half is unphysical, but there is no unphysical half of a correct equation. If the mathematics works, if the equation predicts reality with perfect accuracy, then every part of it is telling you something true. The Dirac sea is real. The vacuum is structured. Space-time emerges from quantum information, and we knew this in 1928. We just didn't believe it. That's the tragedy. Not that we couldn't solve the problem, but that we were handed the solution, and we threw it away because it didn't match our intuitions about how reality should work. Physics doesn't care about our intuitions. Reality doesn't care about what we find aesthetically pleasing. The equations speak, and when they do, we should listen especially when they're telling us something we don't want to hear. We ignored the Dirac sea, and we lost quantum gravity. Now, 100 years later, we're finally beginning to understand what we threw away. The vacuum is not nothing. Information is physical. Space-time is emergent. Dirac was right. We were wrong, and that mistake cost us a century of understanding. The question now is, what else are we ignoring? What other unphysical solutions are sitting in our equations, trying to tell us something profound about reality, while we dismiss them because they don't fit our current paradigms? The lesson of the Dirac is clear. Trust the mathematics even when it seems absurd, especially when it seems absurd because the universe is under no obligation to match your expectations, and the equations know things you don't. We solved the wrong equation in 1928. Let's not make the same mistake.